project, which is worth a bundle of points. We've got the final exam, which is worth plenty of points. And there are still a couple of homework assignments as well. So, you know, it's not game over quite yet. Homework 12 is due on Wednesday of next week. And so I think that is not yet posted on Blackboard, but immediately after class I'll get that loaded on Blackboard and you can get started looking at homework 12. Okay, well, remember that in class last time we looked at this figure, and I sent you a video link after Wednesday's class to show you how you could make the same figure using Excel. So we did kind of like some hand calculation problems that allowed us to find the optimal demand, the break-even points, and how much profit is going to be obtained at a certain volume of demand. Now, what we're going to talk about today is some other aspects of costs, and we'll also talk about how costs affect the level of production that should be undertaken. Now, take for instance, what if your business was making Twinkies? Then in a situation like that, you could break your costs up into categories. The fixed costs, remember, are those costs that aren't affected by level of production. So it could be the machinery, or it could be the rent that you pay on the factory. Because you have to pay that rent and you have to pay the bank for the machinery whether it's being operated or not. But there are also the variable costs which are affected by the level of production. And so the sugar that goes into the Twinkies, the plastic that's used for the wrapping, the delivery costs, the labor expenses, all of those things are directly affected by how many Twinkies that you'd be making in a month. If we graph the variable costs and the fixed costs, this blue line is the combination of the two. So it's showing the same thing that we saw before, a horizontal line for the fixed costs, where the horizontal axis is the number of units produced and sold, and the vertical axis is amount of money, specifically cost per year. And then the variable costs go up and up the more that you make. And so this blue line is the sum of the two. Sometimes the cost relationships are nonlinear. And think about what's implied by this, the shape of this curve. So what was implied for a linear cost curve is that your variable costs per unit don't change whether you're making 1 unit or 1,000,000 units. But in reality, that's not generally true. In reality, you can get bulk discounts. Like if you buy flour by the bag, then you may pay $1 per pound when you buy flour by the bag. But if you buy flour by a rail car, which is maybe 220,000 pounds of flour at once, then probably you're going to get a lower per unit cost. And so the shape of this curve is implying that the more you buy, the lower your variable cost per unit is getting. You know, it still costs you more to make 1,000,000 things than 900,000 things, but the cost per unit at that higher level of production is lower. So that's why the curve has this tapering shape that it does. All right, so if we zoom in on the figure, if we zoom in on this figure, we're going to zoom in just at that first break-even point. Then that's what we get here. So this is looking specifically at the first break-even point. And remember that when we're to the left of the break-even point, we're losing money. And when we're to the right of the break-even point, we're making money. So that's why they're designating the difference between the revenue line and the cost line as profit. when we're to the right of that. So just a couple of review items here. Revenue is your price per item multiplied by the number of units sold. So that's the money that's coming into you. And at the break-even point, your revenue and your costs are equal. So think about, what if your variable costs are reduced? You had some initial break-even point that was here, but if the slope of the cost curve is shallower, even though your fixed costs are the same, so the fixed costs represent the intercept with the vertical axis, but if the slope of that line is less, that's because you're not having to pay as much for the materials that go into the variable costs. So it shifts the break-even curve to the left. So all of this graphical analysis is just a simpler way, or maybe the simple way to say that is that if your costs go down, then you're profitable earlier. You don't have to make as many units to cover your fixed cost if your variable costs are lower. So by decreasing the variable cost per unit, that shifted the break-even point to the left. Okay, so the break-even volume has to do with the revenue per unit, variable cost per unit, and the fixed cost. FC is fixed cost. So you can find out what's the first break-even point with this formula. The cost curve is lower when your variable cost per unit decreases. Now, that's one way that we think of break-even. We think of break-even as, at what volume does your revenue exceed your costs? There can also be this idea of break-even that's applied when you're considering different equipment alternatives. So there may be two different pieces of equipment, and perhaps one of them is more expensive to buy up front, but has lower operating costs. So you could think of that as maybe like a Toyota Prius. You have to pay more up front, but then because it's so fuel efficient, your operating costs are lower. So that's one option, and in this graph that would represent alternative 2, the one that's more expensive up front, but then the variable costs are shallower. And then the other alternative would represent something that's cheaper to buy up front, meaning it has lower fixed costs, but then it's a steeper variable cost curve. So its operating costs are higher. And so here the break-even point is the point at which one option is cheaper than the other. And so whenever you're considering costs, your objective is to minimize costs. And so what you ought to do in a situation like this is find what is the point that the two curves intersect. And if you are to the left of the break-even point, in this illustration, alternative 1 is best if you're making from 0 to break-even point number of units. And then if you're making more units of that, then alternative 2 is cheaper, because even though it has the higher initial purchase price, its overall cost is lower at the high volumes, because if you're making a lot of units, then the lower variable cost per unit kind of pays itself off and justifies the extra amount you spend up front. So the slope of those two curves is going to determine what is the optimal level of production for a given piece of equipment. So here we're defining break-even as the point at which two different equipment alternatives have the same cost. And we can determine this even without looking at the revenue. All right. So in today's in-class exercise, what we're going to do is consider the case of two different pieces of equipment. Let's just look at it this way. There is some computer-controlled manufacturing equipment and manual control manufacturing equipment. And there's some differences here between them. You'll notice that option 2 is cheaper up front. It's $1.3 million versus $2 million for option 1. Option 1 Because it's more expensive, it's more durable, a 10-year lifespan versus a 7-year lifespan for option 2. And it also retains some salvage value at the end of its useful life, whereas option 2 has none. Another way that option 1 justifies the higher cost is that the labor expenses are lower. The computer-controlled method is only going to cost you $180 per hour that it's operated, whereas option 2 has a higher labor cost per hour of operation. And not only that, the computer-controlled equipment can kick out the units more quickly. Whatever it is it's making, it does it faster. So, for instance, if you needed to make 3 units, it would take you 1 hour for option 1. But if you needed to make 3 units, then option 2 would take 1.25 hours. So think about the amount of time it would take. And since time is money, quite literally, because of the labor costs, option 2 is going to be more expensive, both because the labor costs are higher and because you've got more hours you're spending for each unit that's being made. Okay, so that's the setup. Now the template I'm going to provide, it's not a template file, it's just showing you what it should look like. And so let me show you the template file. This is simple enough that you can just type this into a spreadsheet. We're going to compare these two alternatives under a couple of different conditions. First of all, you should calculate the capital recovery for both alternatives. And do you remember how to do capital recovery? The definition of capital recovery, if you're using Excel, remember you use the payment function for capital recovery, equals PMT. And so when we do capital recovery, we can put in both the first cost and the salvage value, and then it'll tell us the annual equivalent when we know the number of years and the interest rate. Okay, so you're going to use the payment function for both of these options. Now there's no salvage value for option 2, so then that just means that the future value amount into the payment function for option 2, it's just 0. All right, so Part A, calculate the capital recovery. Part B, you'll see that it says, what if it's 1,000 units per year? Then how much are you going to spend for each alternative? So if you want to make 1,000 units, what you're going to have to calculate is, so if it's 1,000 units you want, then how many hours does that take? It's not going to take the same amount of hours. Since option 1 is faster, it's going to be a certain number of hours with the computer-controlled equipment, but it's going to take a greater number of hours with the manual control equipment. So we want to know the total cost. So total cost includes capital recovery and the labor costs. So fixed and variable costs. Okay, so that's at 1,000 units will be option 1 versus option 2. Then you can change in the spreadsheet template the way that you'll have this set up. You're going to put the number of units per year in cell B3. And so for the first problem it'll be 1,000 units. For the second problem it'll be 3,000. And when you change it to 3,000, that's going to change how many hours per year is required. And then that's going to change your variable cost, which will in turn change the total cost. All right, so that's all the hints I want to give you right now. Now, of course, we're going to get back together in about 12 minutes and go over the solution together. But for now, what I'd like to do is just pause, give you some time to start setting this up and translating the given problem statement into the template file and try and interpret how we're going to find out the total cost for these two options. And in case it's useful, I'll put you into the breakout room so that you can check answers amongst each other and talk about the method if you need to. Okay, welcome back. Let's see if you've made the right progress on this one. We'll put it into Excel and try and find out what is the break-even point between the two alternatives. Now in the first case, what we're going to do is analyze 1,000 units per year. So I'll put that in at the top, and the interest rate is 9% for the MAR each year. The first cost of the equipment is $2 million for the computer-controlled equipment and $1.3 million for the manually controlled equipment. 10 years for computer, 7 for manual control, with a salvage value of $150,000 for the option 1 computer controlled and 0 for the other. The labor costs are 180 hour versus 195 per hour. And then we can do 3 units per hour of operation with the computer, or 2.4 when manually controlled. Now this first calculation, it says how many hours are needed to make the expected output. So that's going to be the number of units divided by the productivity. So think about the units here. It's going to be units per year divided by units per hour of operation. So this tells us it's going to be 333.3 hours that the equipment needs to be operated in order to achieve 1,000 units. All right, now if I anchor the reference up here to the desired output, then that allows me to just drag the formula sideways, and it will look at the revised equipment productivity for option 2. Okay, the capital recovery we can calculate with the payment function. So PMT, our interest rate is 9%. The number of periods is 10 years for this computer-controlled equipment. PV, it's asking, the present value is the initial first cost of the equipment. Now, think about how Excel changes the sign of things. You know, so it changes positives to negative in these financial equations. And so I'm going to leave, I'm not going to put the minus sign in like I normally do. And look what happens when I do that. If I just leave it as first costs here, and then the salvage value there, okay, we get 301,000, 301,767 is the capital recovery for option 1. So at this point now I know that this is a cost. So I've eliminated the minus sign just because I know that costs are outflows. Okay. Now, if I drag this formula to the side, let's see, what else am I going to need to anchor? I need to, no, just the reference to the interest rate, which already is. So I can drag that sideways and it'll calculate the capital recovery for option 2. So it's cheaper on a per year basis because the equipment itself is less costly. But then the variable costs are going to be how many hours is the equipment operated multiplied by the dollars per hour required to operate the equipment. So if we're doing 1,000 units, it's going to be $60,000 to operate the computer-controlled equipment versus $81,000 to operate the manual control. So the total cost is the sum of the two. All right, so if we are making 1,000 units per year, then the more expensive option is option 1, and the cheaper option is option 2. So what this conditional formatting is set up to do right now, remember that I think I've demonstrated conditional formatting before. Let me clear the rule that's there now. We can have conditional formatting highlight the cheaper. Let's do it that way just for contrast. The cheaper option is highlighted. All right, so if I select these two and I go here to the Home tab and then conditional formatting, I want to do a top/bottom, and I want it to be, let's see, more rules. Format only the top or bottom ranked value. So it's going to do the bottom one. So the bottom one would be the lowest value, so the cheapest. And then the formatting I'm going to tell it to do is I'll have it fill with the yellow. And so it's going to fill in yellow in the cell that's the cheapest. So you can see the one that's the least is highlighted. So let's write in a conclusion here. If we make 1,000 units per year, then option 2 is cheaper at $339,548 in total cost. Okay, so that answers question B. Question C asked, what happens if it's 3,000 units per year? So let me just write that this was the answer to question B. Question C is for 3,000 units per year. So the nice thing is all we have to do is just change this one value here. $3,000, and bang, you can see that now option 1 is cheaper. So that's changed which alternative is highlighted. So if we make 3,000 units per year, then option 1 is cheaper at $481,767 in total cost. Okay. Now the last thing it asks for in here is use GoalSeek to find the expected units per year that makes them equally expensive. Okay, so here I've got a difference cell where I'm going to find the difference in cost between the two. So right now they're $20,000 different because option 1 is like $20,281 cheaper than option 2. We can do a GoalSeek so that we're looking for the difference to be equal to 0 by changing the outputs per year. And if we do that, it's going to identify this break-even point. It's going to identify the point at which they're both equally costly. So let me do that. Data, what if analysis, GoalSeek. And so my goal is set the difference to 0 by changing the number of units per year, so the output. And as soon as I click OK, what it's going to do, it's going to start playing around with values for this cell B3, which is where our production level is input. And when it finds the exact right number of units that makes the difference in cost equal, it will stop, and it'll just leave that value. All right, so it is 2,045.62 units. Now you can't have a fraction of a unit, so we'd round up and we'd say 2046. And so question D was asking what's the break-even point between alternatives. So the break-even point between alternatives is 2046 units per year. All right, well that is all the time we have for today. Remember that what's on your plate right now is we have a homework 12, which is due Wednesday next week, and then there's also the project. So hope everybody has a great day. I'll see you on Monday. Take care.